So let's take this example. It says consider a cache. The cache has 54 blocks and a block size of 16 bytes. What is the number? What block number does byte address 1200 map to? Right. So now byte address 1200 is in memory, right? But they've given you the conceptualization or the how the cache looks like, how it stores elements. So for example, this is how your memory looks like, right? So let's say this is 1 byte, this is byte 2, this is byte 3, so on and so forth. And maybe by 1200 starts from somewhere here at the top, right? So here is some 1200. Now, if your cache has a block size of 16 bytes, right, and it has 54 blocks, what it means is that your cache, the number of blocks 54. So this is block 1, 64. Block 2, sorry, block 1, right? Block 2, 64 bytes, right? Continually for 64 bytes. However, each block can store 16 bytes of data, right? What it means is that if each one here is 1 byte, right, then it will pick 16 of this and put it in block 1. It will pick 16 of this and put it in what? Block 2 continuously. Do you get it? Now you are to find the block number 1200, the byte 1200 will map to, right? So in that sense, you are finding the number of times 16 bytes can divide 1200, right? Because if you come and divide the 1200 by 54, it's wrong because you're not, yeah, you realize that this is direct mapping, and in direct mapping, the same block may be used by multiple addresses, right? But if you divide the 16 bytes, if you divide the 1200 by 16 bytes, then you are seeing that even if it overflows, right, you know the point at which the 16 bytes may be in the cache, right? So what you do is that you take the 1200, right, and you divide by 16, right? That will give you 75. But see, 75 is bigger than the number of blocks, right? So what it means is that 75 will be in the like 75 will not be in the cache, right? So it means that this number it will compete with someone else, right? But to find what's actual number, you just use the modulo. That's a 75 modulo 64. That will give you 11. You get it? Yeah. So
So 11 is the block number.
yeah, 11 is the block number. So it means that um if the cache was like 16 bytes, infinitely long 16 bytes, right? It would have been stored at what? Block 75, right? But this time we are limited to 64. So we use modulo to bring it what, to the point where it will actually be stored because of our implementation. And that's block 11. Yeah, you have a byte address of 1200. And now you are picking it 64 and 16 bytes by 16 by 16 bytes by 16 bytes. So when will you get to 1200? The 75th times, right? Because 75 times 16 is 1200, right? But the 75th time, you'll be out of the cache memory, right? So use modulo to see where actually it will be competing for. It will be competing for what? Block 11, right? That's what you see. So that's the cache. The next part are just improving the cache performance. I don't know if you should do this, but let's do it. So they realized that for they use two programs, right? We call them benchmark programs, right? Benchmark programs because they used to just analyze the PC performance. So they use one program called GCC, and that GCC uses one word blocks, right? Now they realize that if they use one word blocks, that is the cache at every block, they just use one word, right? Realize that the miss rate was 6.1%, right? The instruction miss rate was 6.1%, and the data miss rate was what? 2.1%. Now the effective, I think they combined both of them and find average or something. Now, however, they realized that when you use word block size, that is, instead of storing one word here, you store four words there, right? The instruction miss rate was what? 2%. And the data miss rate was what? 1.7%. Now see, the instruction miss rate moves from what? 6.1 to what? 2%. Very drastic. The data miss rate was very small. It didn't change much. What it means is that instruction does a lot of spatial locality. You see that when we increase the block size, we will now have four blocks in one. So when we go, instead of fetching only one block, we'll fetch the four blocks associated with it, right? And instructions have spatial locality a lot because usually we just do PC plus 4. Hardly do we have branch instructions or jump instructions, right? So that's why implementing it made that drastic increase. And it can also be seen when you use another program. So they use this program, they use another program, and they realize it's also the same. So you realize that when you increase the block size, it is really good for an instruction cache, right? It might not do much for a data cache. So that's what they are doing. And um, there's also another performance increment. So this one, they were increasing the block size, right? At this time, they were trying to increase the bandwidth of the bus, which fetches from the memory to the cache, right? And they realized that originally this is what you have. This is the original um how what we have been talking so far. This is the organization between cache and memory, right? You have one memory, you have a bus, you have a cache, and the cache is connected to the CPU. Now you realize that if you assume that the cache uses four words, it's a four-word cache. So in each block there are four words, right? Now let's also assume that it takes one clock cycle to send address from memory to the address buffer. That is, you send address from memory to the memory address register, something like that. And also, it takes 15 clock cycles for each data memory access. So like for each location you access, you need 15 clock cycles, right? And then third one is that once you get you access the data, you also need one clock cycle to send the data from the memory to the data buffer, right? From the memory to the bus. So now with this calculation, with these things in mind, right? If you have a forward block, right, you realize that when you are when you are dealing with when you are dealing with this organization, which is one word wide memory organization, right, where the bus is one word, because you are fetching four words at a time for the cache, right? You need what? 4 times 15 data accesses, right? Because you send it one by one. So you need 4 times 15. Secondly, you also need um, 4 times one cycle, right? 4 times one clock cycle for the to send the data from what the bus. So you need 4 cycles because even if you fetch the data word by word, right? You also need for each of the data you fetch because the bus is not wide, right? For each of the word, you need what 4 cycles because they are four words. So one by one, you need 4 cycles to send it to memory. Plus the cycle that needed you to send their address towards memory. Now, in the end, you get 65 total cycles. However, when you make the bus wide, right, now you need still 1 second to send the addresses to memory, right, to find it. However, this time, because the bus is wide, you can fetch all the four in one cycle. Yeah, it will be times 4. So it will be 1 times 15 because when you are fetching, it takes 15 clock cycles per one. But because now you can specify for all the four, your bus is very wide, then you just need what? 1 clock cycle. Then also, because this time your bus is very wide, you also just need 1 clock cycle to send for memory. So in total, you are limited to 17 clock cycle. Now, this is another organization, and this organization says that um, we will segment the memory into banks, right? So different banks of memory. We will not put the memory all together at once, right? Now, the advantage of this one over the very first one is that so you need 1 clock cycle to send the addresses to memory, right? Now, this one, because the memory are separate, right? You can read all the four at once, right? So you just need what 1 times 15. However, because this one the bus is not wide, right? You need what a clock cycle each for sending it from what the bus to the cache. So you come and take this one, come and take this one, come and take this one, come and take this one. So one clock cycle each, right? So in essence, you have what 20 clock cycle, right? And that's the essence.
The last one.
But if it's accessing the memory,
Yeah.
it will still have to use the bus or
If it's accessing the memory, it doesn't have to use the bus. Like there is a buffer for on the memory, right? So like maybe it appears they did not draw it, but the memory has lines. So it appears on maybe the lines of the memory, right? Available for fetch, right? But this bus can only take one of the memories at a time, right? It's not like this bus which can take all the memories at a time. So it's different. Then the performance. So so far when we are dealing with caches, right? The formula for performance is the same, but we also have to consider the stores, right? Because sometimes when you miss, there is a penalty, right? And that penalty will cause your PC to store, like wait a little. So we have the execution cycles. That is the cycles which the PC executes normally, like it's not cache dependent, right? And we have the time when the memory actually stores, right? Like when you are paying a penalty for a hit, a miss on the couch, on the catch, all times for the cycle time. Now the memory store cycle is evaluated as this: the memory accesses times the miss rate times the miss penalty. For now, it's just a bit of this one, but we'll see a formula, a raw example. So let's see an example problem so that you don't get confused. So you have a machine, right? A machine, and the machine has a miss rate of 2%, instruction miss rate. Take note, instruction miss rate. It has a data miss rate of 4%. Data miss rate, right? And it has a miss penalty of 40 cycle always. So we are assuming, right? So it means that whether it is instruction or data you are fetching, if you miss, like the machine will need 40 cycles to recover. Then it has a CPI of 2, right? And this CPI of 2 is that it's like without any problem with the machine, the CPI is 2, right? So you realize that that CPI of 2 will come like will be the execution cycle. Yeah, but let's continue. And it says the frequency of load and stores is what 36% of instructions, right? So the 36% of the instructions do load and store, right? Now this is also important, right? When we are solving it. So it says how much faster is a machine with a perfect cache to that never misses. I think yeah, with a perfect cache that never misses, right? Now a machine with a perfect cache with this one, with what they have given, will have a CPI of what 2 because it has no memory stores. There are no misses, right? So that will be the perfect cache. However, if we are to solve this one, so we want to compare this machine here right now with the machine of a perfect cache of CPI of 2, right? So it means you have to evaluate the CPI of the machine with these parameters. And it's simple. So let's assume that the total number of instructions is what? Right? We don't know, right? But we know that the instruction miss cycles, right, is given by the number of instructions times the percentage of what the ones which are missed times the miss penalty. Remember this formula, right? Now the memory accesses will be the number of instructions here, right? Times the miss. So that's what you see. Now that will give you 0.8i, right? Now remember, not all instructions are load store, and it is only load store which was require memory, at least most of the time, right? So it means that what it means also is that the data miss penalty will only affect the load store ones. It will not affect all instructions. How do you call it? All instructions involve the instruction memory, whether you like it or not, right? But not all instructions involve the data memory. It's only the load store which involve the data memory, right? So that 36% here will only affect the load store instructions, right? It will not affect the whole instruction set. The whole instruction set here, they will all be affected by the miss rate of 2%, right? by the how do you call it? The data miss rate only affect what the load store ones. You get so that once you are evaluating, realize that that one the total instructions should be high, but it's only 36% of them. So you multiply by 36%. The total instructions is high, right? Now this 2% is the miss rate, not the percentage of instructions. Like the total number of instructions is high, but it's only 36% of them which are being missed, right? And the 32% which are being missed, their miss rate is what? 4%. So the 36% are low store instructions. 36% of the instructions are low store instructions, and 4% of them encounter what misses. Huh. Now, when you encounter misses, the penalty is what 40. So you realize that this one is not very different from this one, apart from their difference in what the miss rates, right? And the fact that this one use 100% for the number of instructions, this one is only 36%. 100% is so we don't write it here. Okay. Now you get what 0.576, right? So the total memory store will be what for instructions as well as data, and that's what you add here. So 0.8i plus or 0.576i. That'll give you 1.376i, right? But now this is the memory stores, right? Remember that the whole CPI is supposed to be what execution cycle plus memory stores. So we've calculated the memory stores, so we need the execution cycles. So the execution cycle is what 2, right? It is 2 because the execution cycle is the part without the messages and memory stores. So that would be 2. So we add 2 towards the one with memory stores to get what 3.376, and that's our the okay. So the total memory stores is 1.376. Hope you get that one. Yeah, because you add the one for data plus the one for now the execution cycles is 2 because in the question it says CPI of 2 without memory stores. So without memory stores is so we have to add the memory stores to get the whole execution. Okay. So that's what you do. So even with the data in this one, you have to add what the memory stores. Right. Now when you add, you get to the point 376. What this means is that when you find a ratio of 3.376 and the ratio of what with 2, 3.376 is the one with memory stores. The 2 1 is the one perfect machine, right? Realize that what this machine is the performance with a perfect cache is better by a factor of what 1.68. So it means that if the cache was perfect, right, this machine would not like will have a performance 1.68 times better, right? That's what it's saying. Now there is the second part. We are saying fine. What if we change the CPI? So we are trying to improve the performance of the machine. Realize that when we decrease CPI, the performance of the machine should increase, right? Because remember, assume that here was 1. Let's say truth, here was 1. Realize that we'll get what 3.376, which means that what a machine which has the machine will be better by a factor of 3.376 if they had a CPI of 1 without any misses, right? So now, when we use a CPI of 1, right, the same procedure. However, this time, the 1.376 that we found from the misses of the data in the instruction, we'll add 1, we'll not add 2, because now we've changed the CPI, right? Yes, and now when we compare, we get what 2.376, right? So the conclusion is that um, realize that our performance here, although we decrease the CPI, right, our performance here is just 1.68 times, right? But here it was 2.376 times. What it means is that when you decrease CPI without uh, changing the miss rate or other parameters, right, it is worse because a high percentage of the instructions are actually like affected, right? So that's what that's what is here with higher IPC or lower CPI. IPC is the reverse of CPI. Cage misses hurt more than what the lower IPC. That's all they are saying. Now, when you double the clock rates, I think still using the old CPI, right? They say what if you double the clock rate, right? So if you double the clock rate, the miss penalty will double. The miss penalty was 40. When you double the clock rate, then the missed penalty becomes 2 times 40. So we evaluate the stores again. The stores for what? For instruction, the stores for data. Right. We evaluate again and we get 2.752. Then we come and evaluate the total CPU time. Right. To go forward, the original machine, 2.72 for the what?
This without like
Yeah,
misses and stuff.
yeah, without the misses and stuff. So when we do it and realize that when we when we realize that the performance with a perfect cache is better by a factor of 2.376, we realize that the values keep getting it keeps getting worse, right? And it says so the original machine had what 1.68, right? So it means that it's just 1.68 times better. But when we double the clock rate without changing the CPI, right? It is now 2.376 times better, right? Which means that the performance has gone down actually. So it means that we should increase the CPI without without changing the clock rate, right? You get a worse machine. And if you also change the clock rate without changing the CPI, you get a worse machine. So that's what they are saying. Then so far the cache we have been looking at. So that's what it means. Like when you compare to the perfect counterpart, the perfect counterpart is the two, right? The original the CPI without the miss. The perfect counterpart is the two. Realize that the perfect counterpart is doing what 1.68 better times better. Here the perfect counterpart is the one, right? And the perfect counterpart is doing what 2.376 better, right? So it means that this machine doesn't really hurt much compared to its perfect counterpart. But this machine hurts much compared to its perfect counterpart. And that's it's the language, the way they put the language. But the next one is other type of cache. So far we've been looking only at direct map, right? Caches which have the data in memory only has one association in cache, right? But now we can also consider other types of cache, right? Like fully associative, set associative, right? So the fully associative is that if this is the cache, we don't care anywhere we can put our data. That's fully associative. Set associative is that
So this one is regardless the tag is
yeah, this is regardless of the tag, you can put it anywhere, right? That means that anytime you are coming to locate it, you have to search one by one and find it, right? So that's the cost of this. Now, the set associative is that, well, we'll not do fully associative. We'll also not do direct map. We'll mix them, right? So we would say that instead of all the blocks of cache, maybe we'll break it into sets, right? So it means that some data cannot be found in certain sets, right? So some data, so maybe let's say this will contain maybe only the first four memory addresses. This will contain the next eight, right? And it means that when we are considering data in the first four memory addresses, we'll not come and search here, we'll come and search somewhere here, right? But this one will contain smaller blocks inside, very smaller blocks inside. So we have to search it one by one. So we have to search one by one, just like the fully associative. However, we have only a limited search space. And that's the use of the set associative. Right? So increasing the degrees of associativity reduces miss rates because we have a very large space, right, where we can store a lot of data. Realize that the direct mapping, because everyone is associated with a specific part, right? Even though there will be waste, like space wasted, we still can't store there because we want to associate with a specific part. But when we increase the associativity, we reduce the miss rate because, I mean, when we are bringing data into cache and it collides with this location, we can just put it at the next part, right? It increases hit time because of the parallel search, right? Because you are not putting at a specific location, you don't know where to search for. So you have to look at everything for the associativity, right? So when you increase the associativity, that's what's happening. So they are comparing the three of them. So they are saying that for direct map, right? For direct map, if you had a memory location 12, right, it will always map to this 4. You can't change it, right? So maybe if you have another number like say 24, right? 8 modulo, okay, no, let me take a number which will give me 4 more than 12. Let me say 20, right? 20 modulo 8 will give me 4, right? So when 20 is coming, 20 will come and replace the 12 here, right? That's direct map. Everyone needs that specific location. I can't change it for you, right? Now, this one is what? Set associative. Set associative is that, well, we have divided into sets. So this is what? Set 0, set 1, set 2, set 3. So this is 4 sets, right? Now, because of that, we'll not be doing modulo 8 again. We'll be doing modulo 4 because we now have 4 sets, right? So, for example, this one, the 12 modulo 4 gave me what? 0, right? Now, when I do 20 modulo 4, it will also give me 0. However, I'll not come and replace this one because there is space for person, right? However, if I'm coming to look for it, I have to search both of them. But when it was direct map, when I'm coming to look for it, I just know that it is always here. Like, I don't have to search anywhere again. So you realize that the more you increase associativity, and then this is fully associative, that one it doesn't care. So whether it is 12, whether it's 20, it will get somewhere for it, right? However, when you come to search, you have to search through the whole thing, right? So that's the two. Well, two-way means that the each set contains two elements, right? That's the two-way. The miss rate. Okay. So this one will have a lesser miss rate because, for example, this very same one, if you were accessing like it is down, but let's do it. If you were accessing 20 and 8, like in continuous, maybe the first time you access 20, the second time you access 8, you realize that you'll be always missing because the first time if you count for 20, what is here? 12, right? So you go and replace it with 20. If you count again, what is here? 20. So you have to go and replace it with 12. So you'll be continuously missing. However, this one, the first time when you place it with, when the 12 is not inside and you put 12 inside, right? It's a miss although. The second time you come, you don't find 20. It's also a miss. However, you will not miss again because now 20 and 12 are now both there. You get it? Yes. But this one, I realize that with just these two elements, you always be missing. But this one, you just miss twice and you don't miss again, right? Now this one, I mean, with just two elements, you can never miss, but you take a long time to search. And that's what you see. So, but just take note that when we are doing the modulo for set associative and direct map, right? Realize that this one we use modulo of the number of elements in a cache, but this one we use modulo of the number of elements in the cache divided by the number of what sets we want, the number of elements in the set, right? So the number of elements in the cache is 8, but in a set is what 2. So that's why I use the modulo 4. Right? So just take note. The number of elements in the cache is 8, but the number of elements in a set is what 2 because it's a two-way cache. So we use modulo 4 instead of modulo 8. So, decreasing miss rates with associative block replacement. So here is what we are just talking about, how we decrease miss rates, right? So for a two-way set associative, right? Initially you have an eight block set, right? Like you have a cache with 8 spaces, right? Now, if you implement it as a two-way set associative, then means that for you have 4 blocks now, right? And now each block can store 2 different sets of data. So this is for set 1, set 2, set 1, set 2, right? So in total, you still have 8 locations, right? But the 8 locations are fixed for some elements, right? Now, if you do it 4-way, you have only 2 sets, right? Because 8 divided by 4 is just 2. So you have 2 sets. But so it means that each set will only be able to store 4 elements, right? The upper set and the lower set, each one be able to store 4 elements. Now, if it's fully associative, then I mean everywhere is usable. So that's how they do it. So you can store everywhere, anywhere, right? You store 8 elements. So fully associative is like you have only one set. But yeah, fully associative is you have only one set. So fully associative is an 8-way, right? You can store anywhere, right? So for this type of cash where we are talking about n-way associative and the n is 8, right? Fully associative will be 8-way, right? But set associative can be 2-way, can be 4-way. But direct map is only 1-way. You can only store here. You can only store here. So that's why we call the direct map 1-way set associative. So they all evolve from the set associative, right? But I mean, if you increase the set associativity to some points, then they can store. So there is a question, right? And it's actually what we are doing. It's saying that find the number of misses for a cache with 4 one-word blocks given the following sequence of memory block accesses, right? So now you'll be accessing block 0, block 8, block 0 again, block 6, block 8, right? For each of the following cache configuration, direct map, right? Now when you're given a question like that, take time and find um, how each of the location they have given you will map into cache, right? So now they say memory location 0, right? How will it map into cache? 0 modulo 4, because they say the set is what? It's a 4 one-word block, right? 6 to map into 2 and 8 to map onto 0. Do you understand it? Now we start the whole process, right? So we can just draw a table. Address being accessed. Will it be a hit or a miss? Will it be what is the content of the cache per reference? Right. Now this cache has 1, 2, 3, 4. 4 blocks because it's a what? It's a 4-block cache. Direct map, right? So it will have 4 blocks. Now the first time we try to access 0, right? We try to access 0. It's not already in the cache, so we'll miss it.
Yeah.
So we'll place it in the cache. That's why here is color yellow, right? Now we try to access 8. 8 will map onto what? Block 0 again, content 0 again. Now it will not, the tag will not compare correctly. So it means that what we have to replace the 0 replace there. So we'll write again, right? So that one will also be a miss. The fourth one is that we try to access 0 again. 8 was the one which is there. So we'll miss again, right? Yeah. The next one is we try to access a 6. 6 maps onto what? 2. So 6 will go here. Now 6 was not already there in the previous one. So it's also a miss still. Then we try to access 8 again. 8, 0 is what is at the place, right? So what? We have to rewrite it equal 8. You understand? So when you see memory into bracket 0, it means that originally 0 was there. When you see memory into bracket 8, it means that originally 8 was there. You understand? So you realize that at the end of the day, we make what? All these misses, 5 misses.
You said one is in yellow is a miss, right?
Yes, I mean, so we are rewriting. So this one did not miss here on this block. It missed because you see that this one was 6, right? Now we are not writing the content here. We're writing the content here. And the content here was not already in memory from the previous one. That's why it was what it was here.
Okay, so here, the 0 that was here from this
Yes,
previous one,
that's seeing 0.
it's still there.
It's still
It
there.
wasn't replaced.
It wasn't replayed. Right. So this one, although this we did not get a miss in this block, we got a miss in our block. So it is still a miss for us. Right. So we get a total of 5 misses. Now let's consider a two-way set associative. So a two-way set associative, and 4 divided by 2 is 2. So we use what? Modulo 2. So 0 map onto 0. 6 map onto 0. 8 map onto 0. Right. So a two-way set associative means that we'll be using these two sets. So this set and what? This set 0 and set 1. But since everyone is mapping onto set 0, then means that it is only here which we'll consider. We'll not consider set 1. The first time we tried to access set 0, 0 was not already in memory because this is our first time. So, I mean, it's a miss. So we have to put the 0. The first time we try to access the 8, 8 is not already in memory, right? So that one too is a miss, right? But however, when we come to the set inside, when we come inside the set, already 0 is occupied. So we can put it at what? The other set, right? Like this set is occupied, right? But you can put it at the other. So it means that although we miss, we have put it at a different location. The next time we come for 0 again, we'll not miss. We'll hit because it's still there. So that's the hit you see. The next time we come for 6, 6 is not in this one, right? But what did we recently access? We recently access what? 0, right? So it means that we have to clean the 8, right? So that's the LRU policy you see here. That's what they are saying. That in the case where it has become so inconvenient for you to right? Then it means that write the oldest one that you have changed. It's so we'll put the 6 there. Then we come for an 8 again. 8 is not inside. So what? We miss. So you realize that we do a total of 4 misses. Here we miss what? 5. This one miss 4. Now let's go to the fully set associative, right? So the first time 0, fine, we miss. But we'll put it at what? Block 0. Second time 8, we miss. Right? But I'll put it at block 1. 0, we don't miss, right? 6, we miss, but I'll put it at block 3. 8, we don't miss because 8 is already there. So you realize that this one had only what? 3 misses. So you like the first, it's this one, it is, if you have enough blocks, it's only the first time that you access that it will miss, right? Unless you don't have enough blocks before maybe all the blocks are full, so you have to change the least most accessed one or something. So that's it. And that's this is a way of implementing the set associative. So you have the index to select a block, right? And a block contains a number of sets. So then you use some parallel searching technique. So this is just a parallel searching technique, right? To just get the correct data you are requesting, whether it's this one, or that one. I think that's all for cache. The rest is just reading. Oh, okay, there's another calculation. Let's take our time.